We were just talking about you.
It's like if you talk about him, he'll show up.
Kevin, what did you get?
Okay. So let's first off on that assignment from yesterday. Your first two answers on 1 and 2 both should be 10 to the negative fifth. Okay? The second answer would make an not bad GPA. Okay? That's a relative term.
That'd get me beat.
Or as well it should. Okay, now let's talk about that question number 3. Because this is going to be important today in terms of how you calculate what happens when the magnetic field is in a hoop. So, in this situation, the initial problem is actually like a circle. And this is what I tried to tell you yesterday. I think it's easier if I treat it as a square, okay? Going like this. Makes it a little bit easier to see. So, the y-axis is like this, and then you've got your x-axis, and then you have your z-axis, okay? Now, obviously, it would be somewhat difficult to get it to spin about the z-axis, okay? Mainly because of the fact that it would have to act like a wheel, okay? So spinning about the z-axis, about that, isn't going to happen because there's nothing for it to spin about. So that basically either leaves your x-axis or your y-axis. So it's in the xy plane, it's flat basically, and it's carrying a current as shown. So the current is coming around like this, okay? So that's the direction of the current. And you're trying to produce a magnetic field to produce a torque on the loop so that it rotates clockwise about the x-axis, okay? So, clockwise around the y-axis. So, you want this to spin like this. So imagine that this is, where'd my little hoop of wire go? Okay?
And you need a battery?
So imagine this is the hoop. And here's your z-axis, then here's your x-axis, and here's your y-axis. So you want this to spin clockwise like this, okay? So this is the visual. So you want this side to get pushed down, and you want that side to get lifted up, okay? I can't have both of them being pushed down, because if I have both of them being pushed down, it's not going to spin. Can't have both of them being pushed up. One has to push up, the other one has to go down. Now, so if you look at your options in your magnetic field, so if you start with the idea that this is the direction of the current. So remember, is the current your thumb, the index finger, or the remaining fingers? Thumb. That's going to be your current, okay? So if I take that current, and I'm going to look at that current going like this, okay? So this is, from your perspective, this is tough to do and still view this. So this is the front edge of that current, right? So I want this corner to make it spin like that. I want that corner to be pushed down. So if that happens, if that corner is going to be pushed down, so the current's this way, I want this to experience a force like this. So what direction does the magnetic field have to go? So that magnetic field is going to be going like this, okay? Now, it has to work all the time, right? So if I look at that back side and think, okay, well, does that work over there on that back side? So if I take my thumb and that current down, I'm talking about this corner back up here. So if this holds, it has to hold on that corner as well. So if I put my thumb in that direction, and I think the magnetic field is going into, like that page, then my fingers point upward, and that's gonna lift that side up, okay? So I can't have it only work on one corner of this thing. It has to work on that other corner as well. So it has to drive this one down, it has to drive that one up. That's what allows this thing to spin like I showed you yesterday on the magnet. So, now, what about the ones that are on these sides over there? What's gonna happen to those forces?
They don't really do much.
Why?
Because the forces cancel out and they
No,
go
no. The current's going like this and the magnetic field is going like that.
They go.
Thatch.
They're parallel.
They're parallel. So parallel sides don't have anything. It's only when you're at right angles are you going to have any kind of torque. Makes sense. Okay? Andrew?
Is it strictly right angles, or would it, like, any component
You're
that's at a right angle?
You're just gonna say, hey, this is what it is right at the beginning. So you're just gonna say, hey, it's a 90-degree angle. Okay. Jane Carroll.
Would that mean that's in the positive Y then?
Well, if you look at how this is, the way this thing is set up, right? So, in which direction should an external magnetic field be oriented? So, here's, how do they have that set up? I drew that wrong.
You switch the X and the Y.
It's rotating around the Y.
Yeah, it's rotating around the Y. I screwed that up. Forget what I just said.
Just switch the X and the Y.
I did, I messed up the X and Y. Yeah, I did. So,
Yeah.
that magnetic field for this to go being pushed down, so when it hits this part, so it's got that current right there coming this way, so it actually has to be directed in the negative X. I apologize, okay? I screwed that up. I lost track of what it was spinning and everything else. So that magnetic field needs to be going in that negative X direction. My apologize, the other thing I can blame it, I had surgery on my arm and right now it's killing me. So if I screw things up, I have a little bit of something. All right, on question number 4 on the back. So what you have to do there, and this was the defining moment on how you determined what was, whether it was electrons or if it was protons. So, in reality, since it's electrons that are moving, that's what drives you to this answer. So, if you look at what you've got, give me a second. Okay. The way this is set up, with here's the negative terminal and here's the positive terminal. If it's electrons, what's the horizontal direction of the magnetic field in that plate? Don't worry about the magnetic field. What's the direction of the electric field in the plate?
Right.
Left or right?
Right.
Pointing this way. Why?
Positive is on the left side.
So over here, so this is negatively charged, this is going to be positively charged, right? So when that electron hits here, it's going to be repelled by that negative side, and it's going to be attracted towards the positive side, right? Okay. So as that goes across, but that's for an electron. But how do you define the movement, the direction of an electric field? So, but it's still the same idea. So a proton would be repelled by the positive and be attracted to the negative. So is everybody cool with how the electric field is going to be moving to the right? Good with that. So the horizontal electric field is going to be moving this way. So that's your E field in the horizontal direction. Got that? Now, you've got a magnetic field of dots. Okay? So I want to look at two situations. If it's electrons, okay? If it's electrons, and you use the left-hand rule, so the electrons are going this way. Electrons are going this way. The magnetic field is coming out of the page, right? What's the direction of the force? Down. So what would happen if it's electrons? You would see the bottom side of that plate becoming negatively charged. Okay? Now, if the bottom of the plate is negatively charged, what's the direction of the vertical electric field?
Negative.
Up or down?
Down.
Down. Why? Because if you released a positive charge from up here, it would go in that direction. Now, if it were positive charges, and this is the difference, if it was positive charges, when positive charges went across and you did the right-hand rule, you have positive charges going this way, the electric field is coming out, but instead of driving negative charges down here, you would drive positive charges. So if you drove positive charges down here, what would be the direction of the vertical electric field? Be pointing up. So this is how you settled the debate, was that you looked at the direction of the electric field, not in the horizontal, but in the vertical. And that's what settled the debate. Now, there is an argument to sustain the work of Ben Franklin. Okay, that you can make the argument that he wasn't totally wrong. It's a little bit sketchy, but I'm going to give you the argument. So, basically what happens if you look at an atomic level, these electrons are like playing leapfrog, okay? So, like for example, you have copper. We really don't know what the electrons are doing, but just say that we can. And we have an electron in that first copper atom, and it jumps and it moves to the next electron beside it, or to the next atom beside it, and then it just keeps leapfrogging like this, okay? Well, when it leaves, and this is where it gets a little sketchy, it leaves a positive hole where the electron was. So as the electron moves in one direction, basically the positive hole that it leaves is moving in the opposite direction. So as the electron is jumping this way, you can see the positive charges that basically it leaves behind. It's not the best argument, but it was just some way that you can go, maybe Ben Franklin wasn't completely wrong, because the electron's going to lose like a positive charge or leave a space, and that's what's going to move in the opposite direction. It's sketchy, but hey, they were trying to save Ben Franklin. Very admirable. Okay, anything else on the assignment? We're good? Make sure on number 5 that you have shown me some work. If all you have on number 5 is a circled answer, you are going to miss the vast majority of the points on problem number 5. You better have some type of logical, mathematical basis for your answer. And not just, well, everybody thought it was B, okay? Your mathematical justification can't be everybody chose B, okay? I want a mathematical well-written justification. As Gapshawn erases furiously.
No, I'm adding more. I'm giving you more details because my work was a bit sloppy.
No,
Just a bit.
get out. Okay. All right, anything else? Once, twice sold, get that handed in.
Is it 3 on the back?
I picked an immaculate native. I'm also turning in the physics assignment that I didn't turn in yesterday.
If you look at my chem grade, it's literally all A's. But if you look at my physics grade, it's mostly B's. I'm not that.
Golden Oreos? Oreos on top. What? Golden Oreos on top.
You're gonna agree with that, aren't you?
I do know. That's crazy. The black ones. Hey, are you he's racist.
We now know why Charles likes white Oreos better.
I'm not.
You said it in a way where it's really obvious.
What do you want? I just want to know. Yeah, here, let me know. So I can pay attention. No. Yeah, turn it down. I'll turn it down.
I'm gonna place the bets in.
I don't want to, no.
What is it?
Why did you have a golf ball? Well, because I bounced it to Thatcher, but no, why did you have a golf ball? Because I found it. Yeah. I bounced it to Thatcher. This is very relevant in chemistry about entropy. That is exactly something.
I'm saying like, no, it might be 68.
No, like the fact that he was about to golf ball now is literally entropy.
You talking about his age?
Okay.
You know,
So, let's say,
What? It'll be fine.
so we've got a square hoop in an external magnetic field that's going to the right with a current going around clockwise. Okay? So the first thing I want to figure out is that, so imagine this is the situation. Here's our hoop. Okay, we're like this. We're in this plane, Jane. They didn't mean to rhyme, they just did. Okay? So we're in this plane.
Oh, we're at this plane?
Okay? So so we're like this, and the magnetic field is coming in like this. Okay? So first off, we'll create any torque on the tops and bottoms. Why not, Sydney?
It'd be parallel to the.
It'd be parallel with it, exactly, okay? Now, so if the current on this side is going up, okay, and it is. So if the current's going up, the magnetic field is going to the right. So the force on this side of the wire is gonna do what?
Go into
Go into the plane. It's gonna try and push it like this into the plane. Okay? So, current's going up, the magnetic field is going this way, my fingers are going this way, right? So this side is gonna try and push it into the TV. Now, what about that side over there? Current's going down, magnetic field is going to the right, my fingers point out. So this side is gonna get pulled out, that side is going to get pushed in. Good? Okay, so this would go like this as it spins around. Got it? Good? Okay. Now, at the core lesson, core beginning of torque, okay? How do you calculate torque? Force times radius, we're not worrying about the sine theta part of it, okay? Now, because we have a magnetic field, a current, and a length of wire, how can we calculate the force?
Do the force equals the force equals the thing.
Force equals the thing.
The force equation.
Bill! Oh!
Live is better.
I got a brother-in-law named Bill, and he's annoying, so that's why I think of Bill. Okay? He's a force for annoyance. So that's gonna be my radius, right? Now, here's the most important aspect of how we're gonna define this with A and B. Is A or B going to be the value for L?
Actually, it's L.
L is A.
A is gonna be the
L is
value.
A. L is A.
It's effective to be A.
Oh, be a teacher, you'll make a
B is
difference.
R. B is R.
Yeah, no.
I think it's gonna
B over
be
2 is
B
R.
over 2 is R.
B over 2 is R. B
R.
over 2 is A is
I'm going all in on A.
Be a voice of reason in the darkness of my abyss.
L is A and B is.
L is A,
Yes.
okay, keep going.
R is B over 2.
So,
Yeah.
in this problem, that's going to be A. Now, the radius, assuming that it's spinning about the middle, which we're going to, the radius would be B over
Those.
2. Okay?
It's just the radius, not the diameter.
Go with this, right? It's the radius that it spins about. But wait, there's more.
Oh no.
Would we need to double this value?
Yeah.
Well, that's.
Because one
Whoa!
side's pushing it, the other side's pulling it out, so it's got
Oh, why do we need to double it?
two sides of the square.
Oh, because it's being pushed and pulled. So we multiply this by,
Dos, X.
so we get,
Sorry.
Trace that.
BIAB. Ooh, but
Some B.
when you multiply A by B, what do you get? Ah, you get the area.
Oh, no.
Whoa. Now,
Uh-oh.
it's okay. It's okay, don't flip out. We're good.
I'm flipping
Okay.
out.
So,
I knew we were gonna do
now,
magic there.
if A and B are the same dimension, it would just be what? A squared, or whatever that dimension is. So if it's a perfect square, then this is just gonna be something square. So now, out of all of that morass, what units should you get? Well, what's the basic idea of torque? Newton meters. Or joules, but technically it's Newton meters, it's not joules. Because it's torque, because it's Newton times meters. Okay. Now, here's one little complicating thing that comes out of this. It's not bad. So that's if it's just one wire. If you have multiple wires, like you have like a bound, like a system where you have like 5 wires or something wrapped around it, which will show you what happens like in a solenoid. So if you have like a whole bunch of wires, all you have to do is multiply it by n, which is the number of wires. Okay? It's not complicated, just multiply it by that. Okay, now let's go to the back. Speaking of solenoids, let's go to the back.